All right, you overachieving Trig students. In this video, I'm going to try to show you why matrices are awesome, where they can be used and stuff. But if you get nothing else from this video, I want you to understand that what is in here is amazing. All right, it's just your normal Folgers brew coffee. Oh, cool, you can actually see the reflection of the camera. That's cool. But this has got Fruity Pebbles creamer in it. And it is so good. Oh my goodness. Fruity Pebbles creamer available at your local grocery store. So first thing I want to mention is the dot product. All right, because when we multiply matrices, we are actually taking a dot product several times. All right, depending on the size of your matrix. Now, it's when you multiply these corresponding pieces, all right, and then add up those sums. All right, I did that in the main video that you had to watch. But what the dot product actually represents, right, and these are just two, I guess, length of two column and row vectors. Like this is a row vector, and these are column vectors. But what they represent are are quantities that have both direction and magnitude. So magnitude just is talking about the length of the object, but the direction, obviously it's got a little arrow here, it tells you where that thing is heading towards or where it will go eventually. Anyway, the dot product is a number that it's used to tell how much these arrows are pointing in the same direction. So that's the question. How much, I guess how much do they have in common? But the question is, how much are the vectors pointed in the same direction? Like these two right here are more pointed in the same direction than this one. And this one is more pointed in the same direction, or these two vectors are, than the third one here. All right? But the vectors themselves, they're kind of like your xy coordinates, because these are just two-dimensional vectors. They could be three-dimensionals. You know, it'd be like if you had an x, a y, and a z. Usually z's like you think of as coming off the page, but don't worry about that too much. We're talking about two-dimensional vectors here, just to keep it simple. So let's do the dot product here. We're going to multiply the corresponding pieces. So 3 and negative 4 is negative 12, plus 4 and 3, that's 12. We get 0. Okay. Multiply the corresponding pieces. You get 50, and then 2 and 2, you get 4. So this gives you 54, and that's the dot product of these two that were pointed in the same direction. All right, with these row vectors, it's the same thing. Multiply those two. You're going to get negative 30 plus 1 and negative 3. And that is negative 3. You get negative 30. I think I kind of glossed over. Yeah, so 10, 2, that kind of corresponds to the coordinates of that point right there. You know, over 10 up 2. 3, 4 corresponds to this vector right here. It'd be like over 3 up 4, kind of like your xy's. But here's what we need to notice. Remember, dot products, they give you an idea for how much they are pointed in the same direction. And I really am simplifying this. There's more to this than just these numbers that you see here. The way it works is when the dot product is positive, like 54, the arrows are pointed in the same direction. All right. Whenever the dot product is negative, you get opposite directions. They're pointed away from each other. And when the dot product is 0, you get this going on. All right. These vectors are perpendicular to each other. That only happens whenever the dot product is 0. And the dot product is 0 only when two vectors are perpendicular. All right. So that is dot products in a nutshell. Like if you were, talking about putting some solar panel things on your house, you would want those solar panels to be perpendicular to the sun. Because if you can help it, I know, the world moves around and all that stuff, and so all these angles change throughout the day, but you want the sun to be directly shining on these solar panels if you can help it, all right, at right angles. So that you basically want the dot product of the direction of the sun and the direction of your solar panels. You want that dot product to be 0. There's a lot to it, and like I said, I'm just simplifying it, and these are 2-dimensional vectors. Let's talk about matrices for a second here. All right, matrices, we're just going to deal with, like 2-dimensional vectors, 2x2s. We're not going to do anything with 3x3s here because that takes more time. Matrices can be used for rotating stuff. So let's say you had that vector again, that 3, 4 vector. If you wanted to rotate that thing, say 100 degrees, and you wanted to know what these new coordinates are over here, or the new vector that matches that 100-degree rotation, you need a rotational matrix to figure that out. Or this is one way that it can be done. Basically, you put 100 in for theta, and these are actually going to be numbers, which we'll talk about later. Spoiler alert. Anyway, but whatever angle you want to rotate it by, let's say it's 45 degrees, you would plug 45 in for all these, and these four values are actually going to be a number. All right, it's going to be like root 2 over 2 for all 3 of these, and then negative root 2 over 2 for this one. But when you take that matrix and multiply it by 3, 4, whatever this actually comes out to be, when you do the rows here, column here, when you multiply it, the answer to that is going to be your new position. It's going to be where you want it to be. Okay? So they rotate stuff. And like computer graphics, this is what they use. They use rotational matrices, and they use computers because computers can take an input and spit back an output super quickly. All right, so this is the algorithms for doing such a thing. Here's your same idea. If you wanted to flip this matrix across the x-axis like that, this is what you would multiply it by. All right, this is like a special case of this, I guess. But, those Fruity Pebbles are good. Y-axis flipper, this is the one for that. This is just what can be done. If you were working in 3 dimensions, there'd be a different matrix for rotating the coordinates of 3-dimensional objects somehow, but still, it revolves around the same idea. It has to do with sine, cosine, which is why we love trigonometry. Let me see how long this video is real quick. Yeah, I think I'll stop here, and in the next video, I'll make a separate one that talks about this zombie outbreak thing. Alrighty.